let's lay down some kinematics. So kinematics, hopefully you can read that, is the study of motion. Actually, it's probably more apt to call it the mathematics of motion. Mathematics of motion. So I'm going to make some assumptions here, and those assumptions are that you know the basics. All right. So the first thing you should understand is that you calculate velocity as a position change over a span of time. Okay. So velocity is a change in position with respect to time. Okay. Should be nothing really too new there. And you should also know that sometimes velocities can be changing, and you can look at accelerations as changes in velocity over time spans. Okay, so just for a bit more background, just to kind of make sure we can go to sleep at night knowing that everyone's on the same page, let's review just a little bit. Okay, so I'm going to draw a number line here, because really all motion that we study, at least when we're doing the algebra of kinematics, is linear, and it's really left and right or up and down against, you know, a number line or against set positions. Okay, so we always call anything to the right positive, okay, and anything to the left negative. Okay, now this is if we're dealing with vector values. So I'll just remind you about vector and scalar values here. Okay, so recall from before that vector values have both magnitudes and directions. Okay, and scalar values have magnitudes only. So if you're asked to give a velocity, you're talking a vector value. If you're asked to give a speed, you're talking about a scalar value. Okay. If we look at a number line here and we say that you know, a person starts over here and they move over to here, we can talk about their motion in terms of a displacement. Okay, so we would call this the initial position. Usually that's still given with a d, even though a position really isn't a displacement. The displacement is the change in two positions. Okay, but still often we would call that the initial position, but we would indicate it with a di. These aren't like set in stone, you know, indicators. It's more the concept that I'm talking about. And their final position would be df. Of course, delta d is always found as a final minus an initial value. Okay, so in this case we would have 6 minus -5, which gives you a positive 11 as the displacement. Okay, so the displacement in this case is a move from this position to this position, and it's 11, and I guess we could say these are meters, 11 meters. So if we want to use this to find a velocity, and we know that, say, I don't know, say this motion happened over a period of 10 seconds, okay, we would say the velocity in this case is, you know, it's that delta d, that displacement divided by the time, so 11 meters over 10 seconds, we get 1.1 meters per second. Now, something else I want to note here is how I'm going to be writing meters per second. So I'm gonna change the old slash to kind of sort of a more universally accepted way of doing that, which is to put it to the power of -1. Okay, so you have to get used to seeing it that way. From time to time, like on old worksheets and so on, you'll still see the slash way of writing that, but we're going to go to this way all across the board. Okay, this is kind of like the international way of doing it, and when you get to university, you'll most likely be dealing with this way of writing this. Okay, so there we go. Now this is for constant motion, right? But it's possible that this object is speeding up, right? And just before we do that, though, One more thing I want to mention is graphing this motion. Actually, yeah, let's do that first. So the first thing we'll write here is we'll write ourselves a position time graph, okay? But again, I'm going to call it D, okay? This is position versus time. That was 10 seconds, okay? And the person started at -5 and ended at +6. And they traveled at a constant velocity because, not because that's indicated by anything I did, but because I'm saying that, okay? So this is what's going on there. So there's your position time graph. The person is traveling right, okay? We have a positive slope on our graph, and their motion looks like this. So what I want to do is I just want to remind you of something, and that is that velocity is found, okay, as the slope of this graph. Okay, so velocity is the slope of a position time graph, or displacement time graph if you want. Okay, how do I know that? Well, I know that any slope, the definition of slope, is always a rise over a run, right? So what's my rise here and what's my run? If you look, my rise is my change displacement, right? Delta t, that's my rise, right? So my delta in the y direction, my change in the y direction, divided by how far I went in the x direction. Or in this case, again, delta d over delta t. So it's the slope. Velocity is the slope of a position time graph. That's correct. Yep, and we worked out that this slope was 1.1 and it's positive. Just one other thing here, right? In math class, we have like y equals mx plus b, notation for this. In physics, we're essentially using this in the background, but these now like mean something. This is a generic math way of doing it, but in this case, y means something. So y is essentially your initial position, or if you want, di, right? That's, oh no, sorry, that's not right. My mistake. The y value is the change, right? Y value here is delta d. It's the change, right? Y value is the delta d. The slope is v, okay, and the time is t. So we could say delta d equals vt, and all we've done here is we've rearranged the formula that we were working with before, right? Let's put a little delta in there so we know we're talking about delta t. Okay, so we've just rearranged this formula. We've multiplied t off the bottom, and we get that, okay? So we want to be even more, we want to tie this into math class a little bit better even. We remind ourselves that df minus di is equal to velocity times time. I'm just going to leave the delta off time, okay? So we know it's a time interval. It's not an instant in time. It's the time that this happens for. Okay, and we're just going to rearrange it. We could actually find df as equal to vt plus the initial position, right? So this looks remarkably like y equals mx plus b, okay? Here's our intercept. Here's our slope, okay? And here's our y and x values. Well, x is time, right? And here's our final position. So just want to have that like little crossover from math class, because you often, you study y equals mx plus b, but you might not like realize the real life applications of it, right? So here it is. It's just a way of describing this motion. There's lots of places you can use this, but here's just one example of it. If I want to know where I am, I put where I started from, I find that slope, and I multiply the amount of time. The nice thing about this is I could extend this off into the future, right? If this person continues, traveling at this velocity, at any time down the road, I can figure out where they are. Okay, so the other thing I want to write here, so let's just put this over on the side. We've got our displacement time graph that looks like this. The next thing I want to talk about is what does our velocity time graph look like? So here's our displacement with time, or our position with time. If we were to draw a velocity time graph of this, what we would find is we get a constant velocity all the time. That makes sense because this this graph's slope never changes, right? Remember, slope is velocity. So if the slope never changes, the velocity never changes. So we could say then that this person holds a 1.1 meter per second velocity the whole time that they're traveling. Okay. That also means that there's no acceleration, but we'll get there in a second. So I want to show you here, just so you understand and make sure that you like lock this in, that there's a relationship going on here. The slope of the displacement graph gives you the velocity graph. Okay. And then we're going to take a next step, because we also said this up there. We said A is change in velocity divided by change in time. Okay, so here's my velocity time graph. Well, I can see there's no acceleration because my velocity is not changing. However, I can still draw a graph of that. It's just going to be a boring graph, right? It's going to be a graph that says, well, there's just no acceleration here. It's zero. There's no slope here. There's no acceleration there. But we're still finding the slope, right? Change in v, right? Rise over run is that slope. So the slope of this graph gives me this graph. The slope of this graph gives me this graph. All right, pause there for a second. So something else that we can note here, right, is that we can rearrange our formulas that we had, right? So again, to remind you what they were, it was delta d over delta t gives me that. But I could actually rearrange that to say that a change in displacement should be equal to whatever velocity I have times time. Now, the way to think about this, I think, is pretty easy. If I travel at 100 kilometers per hour, I don't know, for 3 hours, my change in displacement from where I was will be 300 kilometers, okay? So not to say necessarily I'll be at a point called 300 kilometers, but my displacement will be 300 kilometers, be 300 away to the right in that case from where I started. So what we could say then is, if I look here, right, here's my velocity, here's the velocity that I have, here's the amount of time that I have it for, right? So if I say velocity times time, what I'm actually solving for is an area, and that area is this right here, right? So here's the size of my velocity. In this case, it's 1.1. Here's my time. In this case, it's 10 seconds. So 1.1 times 10, I'll get 11 meters, and that's the area under this graph. Okay, so this delta D, this change, right, this 11 meter change here to here, is found by doing a multiplication of velocity times time. And so what we're saying is then, to work back from here, the area under the velocity time graph equals the change in position, whereas the slope of the position time graph gives me the velocity. Okay, we can do the same thing with this, right? We can rearrange. We say a change in velocity, how much my velocity changes, is equal to whatever my acceleration is times the time that my acceleration works for. This is going to be important in a couple minutes when we derive some new formulas. Okay, so we'd say then the area under an acceleration time graph gives me the change in velocity, not the absolute velocity, but the change in velocity. Okay, so that's kind of some important background information. So we're looking at, really, the whole time we're looking at this motion, right? Someone did this. We've represented it on a number line. We've represented it as a position time graph. Then we've seen what that looks like as a velocity time graph, and we know that there's no acceleration, so we have a really boring acceleration time graph. But we've looked at the relationships between all of these things, okay? So that's sort of our starting point. This is kind of where like grade 10 more or less kind of ends, all right? Then we get into accelerated motion. I know we touch on it a bit, but I don't know if we look at it quite the same way. So accelerated motion. Now you might see this in a case where now instead of having a flat number line, let's say we put an object on a ramp. Okay, say we have a ramp like this, and you know, we put a little ball on the ramp. You can imagine that as the ball rolls down the ramp, it's going to gain some speed. Okay. Oops. You can call this 0. Okay. And we know its velocity at the beginning is going to be nothing, so we're just releasing it. We know down here it's going to have some higher velocity. So something higher than 0. We know that at any time we look at it, its velocity is going to be different from when we looked at it before, right? Its velocity is higher here, it's higher here, higher here, higher here, and so on. At any point, at any instant in time, we look at what velocity this object has, we'll see that it gets higher constantly. Okay, its velocity constantly increases. So it's possible maybe that it takes 1 second to cover this, but only like, 0.75 seconds to cover that. Or another way to look at it is, in the first second, maybe it covers this. In the second second, maybe it covers this. And in the third second, maybe it covers that. So it covers 1 meter in the first second, then 2 meters in the second second, then 3 meters in the third second, and so on. So we can see here that its velocity is increasing as it goes. Okay, so we have an accelerated motion. So if we take that and we're to put it on a displacement time graph, you get something that looks a bit different than what we had before. Now remember, calling this 0 and 1 and 2 and so on is completely arbitrary, right? I could have made this 0, right? I could make this, I could make this go the other way. You could have negative and positive, but in all those cases, we're going to have an increase in velocity, right? Whether we call that a negative increase or a positive increase simply depends on which way we define as a positive way for this object to roll, okay? So in this case, we're going to define it to the right. It's going to be positive, and it started at 0. So we're going to get a gradual increase in our velocity. We're going to get a curved displacement time graph, or a curved position time graph. And now why is that? Okay, so just to make sure we understand that, we said in the first section, in the first section here, it covered 1 meter after the first second, but then it was all the way to 1 to 3 meters by the second section, right? So now, yeah, it's not very good drawing. Hopefully you get what I mean. Okay, after the second section, it's all the way to 3, and then by the third section, it's at 4, 5, 6. Okay, so it's increasing the amount of distance it's covering every time. All right. What that also means then, if we translate that over to a velocity time graph, like this, that we're going to have an increase in velocity as time goes by. Okay, like that. And we also now have an acceleration. Okay, so let's draw that as well, and then we'll go back and just look at how we can understand all this. Okay, so the slope of that gives us this. Just gonna have something like that. Okay, so what are we looking at? Well, to find the slope of this graph's a little bit difficult, right? It doesn't have a constant slope. You can't just do a straight rise over run on a curved line. So in order to find the slope here, you're actually gonna have to draw what are called tangent lines. So like in math class, where a tangent line is basically a straight line that contacts a circle at some point. And the way to draw that, just reminding you, in math is if we have center of the circle and we draw a line, we put a 90 or a line that's at a right angle that touches the circle, we'll have a tangent line to the circle at that point. Does that make sense? So we can kind of do the same thing here. Now we're not on the radius of a circle because we have an always increasing line. But the concept of how a tangent works is the same here. So right at the beginning, oh, I want a straight line. Right at the beginning, we have a 0 slope, right? Velocity is 0 when we start, so we should have a flat line. There is no slope at the beginning. A little bit later, we start to get a larger slope, okay? So what we're doing here is we're finding what's called the instantaneous velocity, okay? And you probably would have touched on that in grade 11, well, it definitely would have been grade 11, or a little bit maybe in grade 10. So this is the velocity at an instant in time, and it's found as the slope of a tangent, okay? Sort of important that you know this, all right, because it explains how we get this graph from this graph. So what we're doing is we're still doing the slope here, right? We're still taking the slope. It's just that that slope is constantly changing, in this case, increasing as the object moves to the right, okay? And that will give us a constant velocity increase. And from that, we can now solve for acceleration, right? So the slope here, of course, is the change in d over the change in t. The slope here is the change in velocity over the change in time. That's giving me my acceleration. And we can now work back, right? We can work back from here. So if we rearrange this formula and we say that delta v is equal to acceleration times time, now what we'll do is we'll find that the area under here tells me how much my velocity has changed with time, right? So now we've got area. So exactly like we had before, it's just now we actually have an area under here, which gives us a change in velocity, okay? And then the area under here gives us our change in displacement. But the area is no longer a nice rectangle. It's a funny shaped shape here, okay? So last year, what you would have ended up doing is you would have solved for the area under here, and you would have said the displacement change, the change in displacement of this object, is Vf plus Vi over 2 times t. Okay, that's a way to find the area under here. So what are we actually doing when we do that? This is again review. Here's our final velocity, right up here, some value that we increased to as this ball rolled down. And here's our initial velocity down here at 0. Okay, if we add these together and divide by 2, okay, essentially what we do is we make half of this area, right? Well, if I have a rectangle that looks like this, I can divide it in half in 2 ways. I can either divide it in half like that, right? You can see that here. Here's how I've divided it in half in the middle. Or I can divide it in half this way. So the area under here, blue, the area under here is equal to the triangular area here. Those would be equal areas, right? They're both half of this rectangle. So what we're saying is Vf plus Vi divided by 2 gives me this value here. That's my average velocity. Average velocity times time gives me my change in displacement, how much my displacement changed. So this formula we worked out last year, that when you have an acceleration, okay, when you have an acceleration, you solve for the displacement change this way. Okay. So let's just recap what we know. Okay, this is what's in our arsenal right now. We've got this. We know where that comes from. We got this. We know where that comes from. We have this, which is only for accelerated motion. We actually can do one more thing. Okay, that's we can take this apart. We did this just up there. We could say this: V equals delta D, but delta D is actually like final position minus initial position. Okay, and this is delta T. So we could do a little rearrange here, and we could say this: dF minus di, right, equals V times delta T, right? So we did that rearranging. We could then just say dF equals di plus V delta T. So we're just rearranging that formula. And we could do the exact same thing with this one. Okay, so A equals Vf minus Vi, okay, over delta T, or that rearranges to final velocity equals initial velocity plus acceleration times time. Right? So that's just taking these formulas and expanding them out. So do we really have like 5 formulas? Not really. We have 3, but we can expand 2 of them into something that's a little more, I don't know what you call it, detailed, let's say. All right, so this kind of gets us to where I want it to be. This is kind of a recap of the past. Let's talk about some new kinematics formulas that we can pull out of here now. And there's 2 more that are useful in different situations. Okay, different situations. So maybe we'll start this with an example of one that you might find difficult to solve, at least directly with what you already have. So a car is traveling at 2 meters per second. Okay, it accelerates at 2 meters per second. for 4 seconds, how much ground did it cover during its acceleration, or during the 4 seconds? Okay, so this is a problem that you could actually solve, but you'd have to do 2 steps, right? The first thing you'd have to do is you'd have to find, well, if you know this is the initial velocity, you'd have to find the final velocity, right? And then you'd have to take that, okay, and you'd have to use your formula for accelerated motion to find out how far it went, okay? But what we can do is we can look at this and we can find a way to do it in 1 step, which can be useful in certain situations, okay? So the first thing I want to do is I want to show what this actually is going to look like in terms of both a number line and your little graphs that we know, okay? So here's some, some number line. We don't know exactly where this is on the number line. We have a number line. And we know that this object starts here and it's already moving, right? It's already moving along. It's got an initial velocity of 2 meters per second. And we know that it travels for 4 seconds, but then after the 4 seconds, it's traveling faster. And we could pretty quickly figure out how much faster it is, but I don't want to do that. So what would that look like? Well, if we're taking like snapshots of this thing, right, when it's going slower, snapshots show it closer together, but as it gets faster, they start to spread out, right, as it goes faster and faster and faster. We want to know, well, how much ground did it cover while it was accelerating, okay? So that's kind of one way to look at it. Another way to look at it is, well, we could talk about it in terms of a displacement time graph, which isn't going to help us too much, but it already starts with some velocity and then that velocity increases, right? So it doesn't start with 0, it starts with an initial velocity, so the slope at the beginning is 2 meters per second. We know the acceleration, right? We know that acceleration is 2 meters per second squared. We know that that happens over 4 seconds. So what we want to know is how much that covered. So what will be more useful for us in this case is actually the velocity time graph. Fire that up. See what that looks like. Okay. Here's our initial velocity. Here's our 4 seconds. We have some final velocity. So our initial velocity was 2 meters per second. Okay. And we know that we have a final velocity that's like up here somewhere. And we know what the slope of this graph is. The slope is, of course, 2 meters per second squared, right? Slope of this graph is acceleration. What we can put in here is we can say, let's move that over a little bit. Just trying to make it look nice, you know? There's a lot of like freehand, it just doesn't look that great. So there's my final velocity. So now remember, what we're looking for is we're looking for the change in displacement, right? If you remember before, change in displacement is found as the area under the VT graph, right? Area under the VT graph. So if you look here, you can see that you could find the area of a shape like this by doing 2 things, right? You could find first the area of this little rectangle. Let's fill it with like orange dots. And you could add that to the area bounded by this thing. It's triangle. Blue dots here. We'll call this like area A. We'll call this area B. So if we can find the area here, we should be able to find our displacement change. Okay? So if we look here, this is our initial velocity, right? 2 meters per second. There's our final velocity. We don't know what it is yet, but we can figure it out. Okay? And we know that this right here is delta V, the difference between those 2 things. Okay? So let's find the area of B first. It's easier. Area of B is just simply this. It's initial velocity, 2 meters per second, times time. In this case, that's VI times T, 2 meters per second, times 4 seconds. That's 8 meters. Okay, that's something you'll notice with this this way of writing. Seconds to the -1 multiplied by seconds cancels off. so we end up in the units that we want. Okay, so what we're really saying here is if this object didn't accelerate, it would at least cover 8 meters during the 4 seconds. Okay, but it does accelerate, so it covers more than that. Does that make sense? So now the second thing is we got to find the area of this. Okay, but we got to do it without cheating, so we can prove that it's true. So this is delta v, right? The height here is delta v. So we could also write that as vf minus vi, right? Vf minus vi. So that's the height. And we want to multiply that by t, and we also want to divide it by 2. So let's just explain and make sense as to why that is. So here's delta v, the height. Okay, so we're trying to find this area under here. So here's the height. Okay, here's the time. So vf minus vi times t should give us this whole rectangle. And then, or I guess maybe square if you want, but yeah, we'll say a rectangle. But then we want half of that, right? Because we're finding like the area under a triangle. So vf minus vi over 2 times t. Okay. So just let me write down area A here. So we're going to find area A, right, using this, vf minus vi. So that's the height here, times t. That gives me the whole rectangle, divided by 2, because it's the area under the triangle. It's like half the rectangle. So let's write it like that, and then we'll pause. So I just want to work on this a little bit before we add it. So I want to put it into a format that that looks a little bit nicer. Okay, find a formula that looks a little bit nicer. So the first thing I'm going to do is I'm going to pull the half out. I'm going to say this is the same as saying 1/2 vf minus vi over t. Okay, I'm going to remind you that before we learned that a change in velocity is the same thing as saying an acceleration times a time. Okay, or vf minus vi is the same thing as acceleration times time. So if I see vf minus vi, I know it's equal to a times t, and I can do a substitution. So wherever I see vf minus vi, I can put an at in there. So now we get this. Area of A is equal to 1/2 at times t, which is like saying 1/2 at squared. So now what we're going to do to find that delta d equals a plus b. So delta t equals vit, right? That's how we found this like rectangle, vit, plus 1/2 at squared. And now what we've done is we've derived ourselves a brand new formula. We'll just go look at how this stacks up. So delta d equals vit plus 1/2 at squared. Okay. So let's just go back. I know you're not done writing. Just don't write for a second. What would my final velocity be here after the 4 seconds? If I started at 2, accelerate 2 meters per second every second for 4 seconds, what am I going to end up at? What's my increase in velocity? So for 4 seconds, I go 2 meters per second faster, 2 meters per second squared faster. I must be going 8 meters per second faster than I was, right? After this second, I'm going 2 more, then 2 more, then 2 more, then 2 more. 4 times 2 is 8 more. So I must be actually at 10 meters per second here, right? I'm at 10 meters per second here. I know I covered 8 meters down here. So 10 minus 2 is 8 times 4 should be what? 32 meters, I believe, right? Does that make sense? 2 to 10, okay, 8 times 4, 8 times 2 is 16, double that, 32 meters. I should have gone a total of 40 meters. Hang on, I forgot something. I got to also divide it by 2, don't I? Because we just want this area. So it should actually be 16 meters. So my total then should be 16 plus 4, 24 meters, right? The area here is 24, okay? Does that make sense? So 8 times 4 divided by 2, this is area is 16 and this area is 8. So let's see if that's what we get, just to prove that this works. So 8 meters per second. Oh, I'm sorry, not quite right. 2 meters per second, that's my initial velocity, times the time, that's 4 seconds, plus 1/2, my acceleration was 2 meters per second squared for 4 seconds, square that. So we've got that 8 meters, that's the rectangle area, plus 16 times 2, 32, but half of that is 16 meters, and there we go, 24 meters. Perfect. So it works. So this is a new formula. You'll find this on your formula sheet. You can add this to the other ones that we already have. Okay, so we've developed a new formula and hopefully proved to you that it's legit. Okay, now we have one more formula to derive. Okay, and this would be if we have this problem. So our example problem is going to be this. A car is initially at 2 meters per second and accelerates at 2 meters per second squared for a distance of 30 meters. Find its final velocity. So that's something that you can't really solve directly with anything that you currently have. Okay, so let's remind you of a couple of things. So we have that. Okay, and we also now have this. And sorry, you don't actually even need that one. You need this one. You also have this. Sorry. There. Vf equals Vi plus At. So what we're going to do is we're going to just do a little rearranging here. And what we'll do here is we'll rearrange this to solve for t. Okay? And then we'll plug the t into that formula. So we have Vf minus Vi equals acceleration times time. Okay? Or that time is equal to Vf minus Vi divided by A, divided by acceleration. Okay? We're going to take that, we're going to substitute it into here. Okay. So, I mean, technically we kind of could solve at this point, right? Because we've got rid of t. But this is sort of a fairly kind of ugly way to look at this. So let's do some work with it. Okay. Okay, so the first thing that I kind of want to do is I want to get rid of the 2 and I want to get rid of the a. So we're dividing by 2 and we're dividing by a. So let's multiply by them. Okay, so what we'll get is this. We'll get that 2 AD equals VF minus VI. Oh, I'm sorry, this should be plus. My mistake. Should be plus. Times VF minus VI. So have you guys seen a problem like this before where you have to multiply something like this together? What method do you use to solve something like that? Right, you take the first one, you multiply it by that, then by that. Then you take the second one and multiply it by that, and then by that. Okay, so what you get here is VF times VF. So you get VF squared. Okay, and then you have VF times negative VI minus VF VI, right? Plus VF VI. And then VI times VI. Okay, so a negative plus a positive is the same thing. So you get this, VF squared minus VI squared. And all of that is equal to that 2AD from before. So if we rearrange this, we should get this. VF squared, okay, equals VI squared plus, because we're going to add it on, 2AD. We've now just derived ourselves another formula that allows us to solve a problem like what we saw up there. Okay. So hopefully you can follow that. If you sort of missed what happened, basically all I did was add vi squared onto 2ad and rearrange it so that vf squared was up front. Okay, so a little quick algebra there. So then to solve a problem like we showed you right there, we said that the car was initially at 2 meters per second. So 2 meters per second, we squared that, plus 2 times its acceleration, which was 2 meters per second squared, and it covered 30 meters while it was doing that. So we've got 30 times 2, which is 60, times 2, which is 120, is 4. We should have that it covered, or sorry, that its final velocity is the root of 124, which should work out to be about 11.1 meters per second. Because 11 squared is 121, so yeah, that makes sense. And that's it. So let's just round up what we have now, okay? This will be the last thing here. Let's just round them all up. So you've got this. Velocity is delta d over delta t. You've got this. Acceleration is change in velocity over change in time. We also have Vf equals Vi plus At. Okay, that's for accelerated motion. We have this formula for accelerated motion. Oh, sorry, I'm using S. That's not going to help you. We have T equals Vf plus Vi over 2 times T. It's kind of where we ended off last year. And now we have this. We have for accelerated motion that the distance covered is Vit plus 1/2 At squared. We also have that your final velocity squared is equal to your initial velocity squared plus 2 AD.